Hello, this is Marvin Glotfelty. I'm a hydrogeologist and licensed driller from Arizona, here with another NGWA industry-connected video. Today I'm going to talk about depth-specific sampling, pilot hole, and how we analyze them. This was um, described in some detail in my book, The Art of Water Wells, but I want to just give a quick overview because in that appendix we kind of got into the weeds on some details and things, and maybe just an overview would be a little more useful and give you the concept of how this can work, why it can work, why we would do it. So I've got some PowerPoint here to make it clearer, hopefully, as to how this can happen and why it happens. So in a larger borehole, we would drill a pilot hole with this maybe a 15 to 17 and a half inch bit like shown on the left. Later ream it out to its final borehole of maybe 24, 26, 28 inches. So this gives an example of flooded reverse drilling in a larger borehole. But keep in mind, and I'll try to make this clear as we go, this can also be done in an exploratory boring. The first, a lot of these analyses we first did in slim holes, 6.5 inch to 7 7/8 inch diameter, and then we later refined it and began to use it in larger production wells. So it works in both. It's the same information, just depends on what you're doing. The reaming part, of course, would only happen in a larger production well. But either way, we have our smaller diameter hole here. This first thing we're going to do is drill it down. We're going to log the cuttings. We're going to know what our cuttings are at various depths here. So we might have a stratigraphic column like this where we could cartoon up, right? And then we might do a suite of geophysical logs so we get even more information. So now we can correlate these spikes here with the actual sand units and know some real good details. So at this point in time of the process, we know about our geology, not extrapolated from nearby wells, but in this hole. We know we look at our cuttings, we look at our geophysical logs, so we know our geology. And we can estimate where our pay zones are going to be, but it's just based on the geology. And like I've said many times, in our business, we need to keep in mind the little bit that we know and also the great amount that we don't yet know. So in this case, we know about the geology, but we don't know about the hydrology, and we don't know about the water quality. So next step would be to look at those other things. From the geology, we might pick somewhere between 5 and 10 different depth intervals that we want to focus on, because those are the places where we think that make most of the water. That's where we would want to collect this additional information. So we install our drill pipe, but instead of a bit, we have a perforated pipe on the end, just slotted, maybe torch cut, just some sort of pipe on the end with pea gravel beside it. Now, in a smaller borehole, this may be straddle packers, inflatable packer below, inflatable packer above. That's done very readily. But in a larger borehole, we have the room for a bentonite seal above and below with this pea gravel. Now with flooded reverse, remember we're drilling with almost clear water. We don't have a big heavy wall cake here, and so we have water seeping out to the formation, our construction water. We don't want to sample that. We want to sample the formation water. And so what we'll do is we'll airlift or pump, usually for about 12 hours. That's a long time, but we want to be sure that the sample we collect, because that's a real important sample. It's going to be like, do we have, I don't know, a constituent of concern, high arsenic, high fluoride, something like that, or is it just fine? We'd like to know on each of these depth intervals. Once we're done with this depth interval, we just pull the pipe up to the next zone, backfill with pea gravel and so on and so forth. When we ream out the borehole, all this just gets drilled out. Very simple. But before we pull up to the next zone, we've now got the water quality. We've purged, we grab a water sample, we send that off to our analytical laboratory so we can know what the water quality is in a depth. And this depth interval usually is about 20 to 30 feet from top to bottom. So then we measure that water level. The reason we do this is sometimes out here in the aquifer, the static water levels vary. We have a thing called the vertical hydraulic gradient, and that impacts the way our well performs. So we want to keep that in mind. So we measure that water level, easy to do. We've already isolated the interval. We've done the hard part. And this static water level in this zone may be different than the regional water table. So that's why we do that. The last thing we do, we like to measure the hydraulic conductivity. That's basically the flow characteristics of this aquifer. So if we pumped it, it would produce water approximately equal to the amount, to the velocity that it would take water if we added. So we can do a thing called a slug test, where we hang a pressure transducer down here. And a pressure transducer is handy because it can measure water levels really fast. We can hook it up to a laptop computer. It measures about 1 static water level per second. And then we pour a couple of 5-gallon buckets of water. We make a little mound on the water table, and that mound flows out into the formation. So it happens pretty quickly. Here's a photograph of it happening. This is my associate, Riley Trickey, pouring water into a drill pipe. We have a pressure transducer here, laptop computer, same setup over here, where we can usually we'll do between 2 and 4 slug tests and get repeatability of our data. And this is what it looks like. Even if you pour slightly different heights of mounds, it's the slope that matters. And so we can do this. And so that means that for all these depth intervals, we know both the water quality and we know the flow characteristics. So we can guess at how many gallons per minute it's going to make, as well as what's the water quality. Without all that stuff, how can we know what our final composite well is going to perform like? So now we have the information. It's not everything, but it's pretty good. So we know the flow characteristics, we know the water quality, and we know the geology. So now we're ready to do our math. And the math is not really that complicated. So we have a zone here. Q1 is the flow that we estimate. C1 is the concentration of our constituent. Let's say it's nitrate. So we have a concentration of nitrate. We have a different flow and a different concentration of nitrate. What will happen when they blend? You just do this mass balance here. So this is the first concentration times the proportion of flow plus the second concentration times its proportion of the total flow. And that's just the simple math we do. If we have in this example 2 different zones. If we have 12 different zones, we have 12 different ones that are added together. And so we can give a prediction of what will be the result of the well before we've spent all the money of our client to install it. So here's our track record, just a dozen examples. Now the blue is what we predicted, and the red is what really happened. So you can see that it's a good guess, but it's not, we don't have surgical precision here. We're off by a little bit sometimes. So like number 3, number 10, we're off a little bit. But as long as we keep that in mind, then we'll be fine, because we know that our estimates are reasonable. Here's water quality. Here's nitrate. And these are the same wells. Here's fluoride. Sometimes high, sometimes low, but whatever it was going to be, we were able to predict it ahead of time. And as you see here, sometimes we miss the boat, sometimes we're pretty much dead on. So in general, though, this is a good approach. Here's TDS. So we have found we have a pretty good track record to rely upon. That means that with this approach, we have a way to look at these things. One thing to keep in mind, these examples I've shown you, they are for alluvial basin wells. If you're in a fractured rock formation well, you isolate intervals, they may be connected vertically out in the formation with other depths of the well. So things are a little more complicated. Be careful about trying to apply all this as I've described it to fractured rock formations. But in alluvial basins, it's a good approach, and we've been doing it in my firm for over 20 years with a lot of success. So seems to be working. Well, thank you very much. Enjoyed talking to you today. Stay safe and and have a good one.